All right, because we were out today, I just have to kind of compensate for some of the stuff that we missed because of lost time. This first part I'm going to go over really quickly because we kind of already took a look at it. Unless you were absent, sorry, but try to keep up. We had three types of chemical bonds: a covalent bond, hydrogen bond, ionic bond, and we kind of talked about each of them. No, deep details, just some very general information you're going to need to know about them. The covalent bond, again, is formed when electrons are shared, makes them very strong bonds. Think about it like my arm attached to my shoulder. Can you rip it off? Sure, but it's going to take a tremendous amount of energy to do that. The next one was the hydrogen bond, which is something called a polar molecule. It has this definition of being like a weak chemical bond. Again, different than covalent bond. In your notebooks, you might want to write strong covalent bond there, or strong bond. The hydrogen bond is formed between molecules rather than between atoms. And usually this is when one molecule is attracted to another because of slightly positive and slightly negative charges, which make it a polar molecule. The best example of this, and this sketch should be inside your notebook, is the example of water. So if we go and we take a look at water here, we have slightly negative charges and slightly positive charges on water. And it makes them attracted to other water molecules. Like this will be attracted to a slightly negative side, like right here, and plop, it forms a hydrogen bond. Now, between the hydrogen and the oxygen, that's a covalent bond. That's a very strong bond. It's very hard to rip the hydrogen off the oxygen. So it's kind of like, my arm being attached to my shoulder versus me holding on to somebody's shirt. Can you break us apart? Yeah, pretty easily. But it's much harder to break off the arm. And then just other molecules begin to become attracted to these positive and negative charges. And they begin to literally stick to one another because of this. Now, moving a little bit more slowly, we're going to the ionic bond. Now, this has to do with them completing their valence electron shell. Don't worry about it. The only thing you need to worry about is an ionic bond. Again, look at that flowchart. Flowchart's super important, the one you guys drew in. An ionic bond, or an ionic atom, is one where it's lost or gained an electron. And that's what's happened with ions. They become charged particles, either strongly positive or strongly negative. So sodium chloride, they still act like a magnet, except they stick together much more strongly than a hydrogen bond. So it's much harder to rip these apart. Still easier than a covalent bond, but harder to rip apart than a hydrogen bond. Now, this one comes to like, oh, well, no duh. Water is a vital component in most environmental systems. Like desert, it's still important, but there's other factors there. But just, again, understand water, very important. Now, there's some properties of water that you're going to need to know, just some very general ones. These down here, assuming it's on Earth, okay, that water is going to boil at 100 degrees Celsius and water will freeze at 0 degrees Celsius. Cohesion and adhesion is something that we took a look at with the Penny Lab, where cohesion is just water sticking to other water molecules. And if I went back to that video, we could literally see water sticking to other water molecules. So this right here, what you're looking at, is cohesion. At the same time, water can be attracted to a wall or to a cup or to your car. You've seen little droplets sticking onto your car. And that property of water is called adhesion. So we'll talk capillary action much later on, but it's related to adhesion. It's just water sticking to something other than water. And of course you have things like acids and bases and pHs. For an acid, really, it's just about the hydrogen concentration. And actually in both of them, it's really about the hydrogen concentration. In acid, you have a high number of hydrogen atoms. In bases, you really have a low number of hydrogen atoms. The opposite of that is kind of true. In a base, you have a high number of hydroxides. And in an acid, you have a low number of hydroxides. pH, or the power of hydrogen, basically measures the balance between hydrogen and hydroxides. That's all it's doing. Personally, to me, this diagram makes much more sense. Right here, if you're at a neutral pH, right at 7, it's the perfect balance of hydrogens to hydroxide. If you combine these two, basically you get H2O, like pure H2O, the perfect balance of hydrogen to hydroxides. But now if you start messing with the number of hydrogens, you start changing the pH. Now, if you have an excess of hydrogen, so more hydrogens, heavy on the hydrogens, you get closer to 0. If you get heavy on the hydroxides, you get closer to 14. But really what I want you to take a look at is the hydrogens. The hydrogens is really what's controlling the power of pH. If you have a lot of hydrogens, the pH is going to drop closer to 0. If you have fewer hydrogens in solution, you're going to get closer to 14. So here's just a scale, again, just taking a look at, again, 7 is neutral. I think this does it better than this does, but if this works for you, it works. pH of 7 is neutral. Anything above 7 is basic. Anything below 7 is acidic. All right, so that's kind of where we're going to leave off.